Hi, so welcome to lecture number 4 in Heterogeneity and Networks. It is the fourth lecture in this series entitled From the Mathematics of Living Systems to Modeling Virus Pandemics. This will be a continuation of what you have seen before, especially in lecture 3, where you saw a mathematical model for infectious disease contagion. So here in this lecture, we will present a way to deal with the connectivity and with some degree of spatial distribution of the population, introducing network structures. We will discuss the role of heterogeneity as well. In the case of infectious diseases, for example, the population can be stratified according, let's say, for instance, to age or risk groups. And we will do that, and we will study the impact on the overall dynamics that we have. So the main sources where you can take a look into the literature, essentially this recently published paper in collaboration with Mayra Aguiar, Giovanni Dosi, and Maria Enrica Virgilito. It has been recently published in Mathematical Models and Methods in Applied Sciences. It is open source, and the main contents of this lecture can be found here. Other suggested references are the book Network Science by Barabasi, that can be also be found in his website in a very, very nice and interactive way. This paper with Belomo et al. Was already introduced in the previous lecture and is a baseline for the derivation of the model that I will show. This paper, a compartmental model for antibiotic-resistant bacterial infections over networks, it was published last year in the International Journal of Biomathematics and introduces also some tools regarding modeling of epidemiological systems in networks. And the contents of these lectures can be also found in this book chapter, Understanding COVID-19 Epidemics, a multi-scale modeling approach, that is going to appear very soon in this Birkhauser-Springer series. So essentially here we will present a multi-scale model that it is schematized in this figure, starting from the within host dynamics at the microscopic scale that describes the dynamics and the interaction between a pathogen and the immune system inside a host. From there, we will then move to the scale of contagion among individuals, single individuals who may interact and transmit and the pathogen. And then to the macro level of spreading across populations, entire populations. So a model recap, just to remember a little bit what you saw in the previous lecture. We will consider a population. Initially, let us think that it is spatially homogeneously distributed. And each individual can belong at each time t to one of the following four compartments. They can be whether susceptible or healthy individuals, infected individuals that are carriers of the pathogen and that can transmit it to other susceptible individuals. Then they can recover or eventually die. So what we will assume is that the recovered individuals belonging to this compartment get a long-lasting immunity and remain in that compartment. So in the time interval under study, they don't become susceptible again. So both R and D are compartments compartments which only have outlet fluxes. Sorry, inlet fluxes. Inlet fluxes. Yeah, there is no outlet flux from R and from D. So each individual is characterized by a microstate that is described by a variable that we call W, that we will assume that it is discretized and that it takes values in the interval 0, 1. This microstate will describe the level of activation of the immune defense. So as you saw in the previous lecture, we will assume that W takes values in this set here, where we assume that we have n risk groups. For example, according to age or presence of comorbidities. Under this scenario, we have that W1 equal to 0 will be the lowest immune system activation level. So it will correspond to, let's say, to the weakest individuals, the most vulnerable ones, while Wn equal to 1 corresponds to the highest immune system activation level. In addition, within the infected compartment or functional subsystem, individuals are also characterized by another variable U, that it is, again, it is assumed to be discrete and to take values in the interval 0, 1, and we consider m possible states for that microscopic variable, and it represents the level of progression of the viral infection, let's say from mild to severe infection. If an individual reaches the state U1 equal to 0, we will assume that this individual is recovered from the infection. So there will be a transition from I to R, while reaching the state equal to 1 implies a disease. So there will be a transition from I to D. We can see this better in this transfer diagram. So each block corresponds to one compartment. The widest one corresponds to the infected compartment. So where we see the states U2 to -1, that are the progressions of the infection from mild symptoms to more severe forms of the disease. And these arrows in colors here represent let's say, the game that the pathogen plays with the immune system. So if we have an infected individual with this state, for instance, UJ, we will have a competition between, on the one hand, the pathogen that will try to proliferate and to progress towards more aggressive states of the infection with a rate beta, while on the other hand, we will have the action of the immune system that will try to contrast the pathogen and to move towards less aggressive states of the infection with the rate gamma. Alpha here is the infection rate, that it is the rate describing the transition from compartment S to compartment I. Here I'm using the superscript K to consider the possibility that in principle the individual may belong to the state WK. So W, remember, that represents the immune state. So the individual has an immune activation level equal to WK. And eventually the infection rate may vary, as we will see later, for different individuals, accounting for heterogeneity. So the system of equations, you have already seen that. Maybe there is a slight change in the notation. Here I'm using subscripts to represent the functional subsystems or compartments. So S, I, R, D. For instance, here F, S, K represents we can think about the number of individuals which belong at time t to compartment S having an immune activation level equal to WK. Yeah. For notice that for the infectious class, we have two superscripts because, as we saw, here we within the infectious compartment we have let's say two microstate variables describing the individual. So here we have state UP and WK. Okay. So since for the recovered and the diseased compartments, we are not distinguishing anymore regarding the immune activation. And so notice that we already sum here over K, so that we already consider the total number of recovered and total number of dead. So, but what if we now add to this system a spatial structure? A spatial structure that will be done through a network structure in this case. So we will consider here that the dynamics takes place within nodes of an undirected weighted network that we'll call it G, that is defined by a pair VE, where V is a set of n nodes and E is a set of edges that are joining some pairs of nodes. Which pairs are linked or joined within the network? Well, that will be given by this adjacency matrix A, whose entries are AIG. So AIG will take values in the interval 0, 1. We can just to have a clear idea. If AIG is equal to 0, that means that there is no link between nodes I and node J in the network. If AAG is positive, that means that there is a link joining these two nodes. And the value that will give us a weight of this the intensity of this interaction. So within each node we will have a subpopulation, and that subpopulation will be divided into the 4 possible classes that we can consider, so S, I, R, or D. And to keep the model as a generalization of the one that we presented above without the network structure, we will assume that each node is connected to itself by a self loop. And we will assume that the diagonal entries of the adjacency matrix are all equal to 1. Then we assume as well that the adjacency matrix is symmetric, so that means that the network is undirected. So then we simply extend our mathematical structure for this case. So essentially the system is the same, but now we have interactions among individuals belonging to different nodes in the network. Notice that here the notation changes slightly since we have added one subscript, I, for all the populations, where I represents the node that I am looking at. So again, for instance here, FIR of T is the number of recovered individuals belonging to node I at time T. So if you take a look to the system of equations and in the literature, you will see that we consider that we have interactions among individuals belonging to different nodes in the network that will be weighted according to the entries of the adjacency matrix, but we don't have explicit movement in the network. So we are not assuming that individuals move from one node to the other, but instead we are assuming that they have contacts in a certain way with individuals from other nodes. So we will consider essentially 4 kinds of nodes here that will be distinguished in terms of 3 attributes that will be the size, the immune distribution, and the multiplicity of each class of nodes in the network. The 4 kinds of nodes that we are considering are households. So households will be assumed to have a size of 5 individuals and will have a centered immune distribution. So here essentially this histogram here describes how we assume that the immune activation level is distributed among the individuals in that node. Other kind of node that we are considering are schools that will have a fixed size of 150 and will have a skewed right immune distribution. So here we are assuming that there are more strong people, let's say, regarding to their immune activation level than vulnerable people. The opposite behavior is observed in hospitals or nursing homes that have a skewed left distribution, while working places are also large regarding the population size, but we also assume that they have a centered immune distribution within that node. So, and now we will play a little bit with different kinds of graphs. And the first one that we consider is the so-called Erdos-Renyi random network that essentially consists of n nodes where each node pair is connected with a given wiring probability P that we have to fix. So how do we construct a random network? So first we start with n isolated nodes, just consider in this case 10 nodes which are isolated. And as a second step, we have to select a pair of nodes. For instance, here I'm selecting node number 2 and node number 7, and I will generate a random number between 0 and 1. If that number is larger than the wiring probability P that we fixed at the beginning, we will connect these nodes through an edge or link. Otherwise, we will leave them disconnected. So if the number exceeded P, so as I said, we will add a link here, and then we repeat the previous step for each pair in the network, that in total we have n times n minus 1 over 2 pairs of nodes in the whole network. So just as an example to see how it looks like, here I'm illustrating a random network with n nodes and the wiring probability of 0.15. I will use through this presentation this color code that is green to represent households. So if this node is a household, it will be represented by green. Then blue for schools, red for hospitals or nursing homes, and black for companies or working places. So just some sample simulations considering a random network of 200 nodes with 195 households, 2 schools, 1 hospital, and 2 working places. So we can think about it as, for instance, as a neighborhood. The total population in this setting is 1,700 more or less, and we are assuming randomly 5 initially infected individuals. So here in this figure we are showing the prevalence of the disease, so how many infected we have for each time t, the cumulative infected, the recovered population, and the diseased population for 3 different wiring probabilities, 0.1, 0.2, and 0.3. So what we can see here is that under a low wiring probability, the number of infected individuals remains quite low. The infection is extinct, and so we don't observe any outburst of the epidemic. But if we increase the wiring probabilities, for instance, here we have for the same setting and initial condition, 3 different larger wiring probabilities, 0.5, 0.7, and 0.9. What we see is that in this case, a larger wiring probability generates a different dynamics, and we have a much larger cumulative fraction of the population that is infected at some point and also diseased. So there is some positive connection between the wiring probability and the level of the epidemic. Yeah, as we will see that in a moment. So, but just for a moment now, let us consider another kind of network that is interesting to analyze. It is the Watt-Strogat small world graph. That essentially it is also a random graph, but it has small world properties such as clustering and short average path length. So I recommend you to the Barabasi reference to where that is very nicely explained. So how do we create a small network, let's say with n nodes? So to construct it, so we create a ring lattice of n nodes and a mean degree 2k. So k will also be fixed. So at the beginning, each node will be connected to its k nearest neighbor. So here, for example, in this case, we have k equal to 2. And so let's take a look to this node. So what we see, or try to imagine, but it is like that, it is that this node is connected to its four closest neighbors. So to this one on the left, and this one on the right. Yep. And the same for every node in the network. Then for each edge in the graph, so we already have the edges here. So we choose a uniform probability and p tilde p to differentiate from the previous one. And with that probability, so we will remove a given edge and we will replace it by a new edge linking another 2 nodes from the networks that will also be chosen randomly from the end nodes. Yeah, so essentially if we don't perform step number 2, so tilde p is equal to 0, we will keep here the situation with a ring lattice, but then when for instance we take larger values of p, so we will remove, for instance, this edge and will be substituted by another one linking this to this one, and so on. For example, in the case of 20 nodes and mean degree 4, so k equal to 2, this is how a small network looks like with the tilde p equal to 2.1. So we compare how the dynamics of the infection evolves in these different kinds of networks. Here, in reality, if we take a look to the red diamonds in these plots, they represent Barabasi-Albert scale-free networks. I'm not explaining them here for the sake of time, but you can take a look in the references. But essentially, so what we do now is to generate these three different kinds of networks. So Erdos-Renyi random graphs, Watts-Strogatz small word networks, and scale-free networks, in such a way that they are parameterized in comparable way. And for each kind of graph, we study how the epidemic evolves in terms of three different measures that are the mean degree, the mean closeness, and the mean betweenness of the network. So essentially, the degree of a node is the number in any network, is the number of neighbors that it has. So to how many other nodes this node is linked through an edge. Okay. So, and when I say mean degree, I'm referring that, well, let's take the mean of the degrees of all the nodes in the entire network. So here, what we are repeating an experiment many different times, generating the three kinds of networks, and so we perform this scatter plot to show the proportion of effective individuals at the end when the steady state is reached versus the mean degree of different networks. What we see here is a positive correlation with a quite clear threshold that separates an extinction to an outburst of the epidemic. Then the mean closeness. So what is the closeness? It is a measure of centrality in a network that is essentially calculated as the reciprocal of the sum of the length of the shortest paths between a node and all other nodes in the network. So the more central a node is, the closer it is to all other nodes. So again, that can be done for each single node in the network, and then we can compute the mean closeness, and what we see is a very similar behavior comparing to the mean degree. So there is a positive correlation between the final size of the epidemic and the mean closeness of the network. Finally, the other centrality measure that we consider is the betweenness. So the betweenness of each single node measures to what extent a node belongs to the path between other nodes. So a node with a high betweenness is a node through which we will pass often when moving through the network. So they are nodes that, if they are removed from the network, will have a large disruptive effect in the transfer of information. Yeah. So, and what we see here, well, and again, we are computing the mean betweenness that it is illustrated here. And what we see here is, again, that there is a threshold, but here the correlation is negative. So the larger the mean betweenness is, the smaller will be the final epidemic size. So let me, okay, essentially that. So let me move to this another experiment regarding social distancing and vaccination. Okay. So how do we prevent the spread of the disease in the network? So here we will compare three different scenarios under a common random graph that we will take it as a sample random graph that we will use through the rest of this presentation. We'll consider a random graph with 200 nodes and a wiring probability 0.9. That random graph will be fixed, and from that random graph we will consider different scenarios. For instance, here, what happens if at a given time, in this case time equal to 100, we implement a lockdown. But there are different ways of implementing a lockdown, right? Just okay. I was checking if I was recording. Okay. Oops. Sorry. Okay. So how can we implement the lockdown? So essentially, we consider three possibilities. So we reduce the interactions within each node. We reduce the weights of the network, so the contacts of the contacts between or among nodes. That will be done by reducing the entries of the adjacency matrix, or we can simply reduce the number of edges that connect nodes. So in this case, for the three possibilities, we consider 25% reduction. And here we illustrate how the prevalence and the cumulative disease evolve over time under the different scenarios. So here in blue, we have the scenario with no control. So if we have no control, look, we have the larger, for instance, here, number of deaths, of disease. And then we have in red the reduction of contacts within a node. Then here in green, the reduction of the weights of a network. So let's say, well, as I already mentioned, we reduce the entries of the adjacency matrix, and this situation here in purple is the most extreme one and invasive for the society, that will imply the reduction of edges. So I will say 25% of the connections in the whole network will be removed. So that is the most invasive one, but also the one that at the end has the strongest effect in preventing the larger number of disease in this case. So essentially, an equilibrium must be found in a real situation to fight against an epidemic between these different possibilities. But what in our setting, so the most vulnerable individuals are those who are more likely to lose in the, let's say, in this fight between immune system and the pathogen who is trying to evolve towards more aggressive state. So the most vulnerable are represented, remember, by a small value of W. So W1. So what if we try to implement some measures, but protecting the vulnerable, and we don't touch the rest of the population? So what can we explore two possible scenarios. So first, to reduce the social interactions for the vulnerable segment of the population. So that will be the alphas over 1, and within each node I. Why this one? Because we are considering individuals with the immune activation state W1. And the other possibility would be to reduce the weights of edges connecting to individuals. So again, here we see the three possibilities, and we notice that the reduction of weights would be, let's say, the most efficient to reduce contacts. So in this case, what are we meaning? hospitals and nursing homes. So in a situation of a disease that is likely to be more aggressive in individuals who are weaker, more vulnerable, have comorbidities, well, a good possibility, sorry, would be to reduce a reduction of the weights linking to those nodes where we have more concentration of these vulnerable individuals. So a final experiment that I will show is regards immunization of the population, for instance, through vaccination. So what if we give more strength to the whole population? So how? So again, we will employ the same sample random graph that we were using, but now we will perform the following experiment. Each realization of the experiment consists in choosing randomly a proportion of the total nodes. So let's say 25%, 50%. Randomly, we will choose a proportion of the total nodes, and within the chosen nodes, we will vaccinate the vulnerable individuals. How do we model that mathematically? So those individuals in those nodes which were selected, who had states W1 and W2 will be moved after vaccination to a higher immune level, let's say WN to the maximum one. So what we do, so that is for one realization of the experiment, and here in these figures I'm showing the result of 200 realizations of the experiment. So in each one we choose randomly the proportion of nodes that will be vaccinated and which nodes will be vaccinated. And so we can see this correlation for the proportion of infected individuals at the end of when the steady state is reached, so the final epidemic size, and the proportion of deceased cases versus the proportion of vaccinated nodes. So we see in both cases a negative correlation with the Spearman correlation coefficient in the order of minus 0.9. And so we see that vaccination has a strong effect. So improving the immune state of the population has a strong effect in reducing both, in this case, infection and deceased. Notice that in this particular experiment, we have not targeted certain nodes. They just were chosen randomly. So the situation would even be better if we target which nodes to vaccinate. For example, nursing homes or those nodes where we know that there is a larger concentration of vulnerable individual. So a summary of what we have done. So we have refined the model that you saw in the previous lecture, and to adding heterogeneous interactions and a network structure. And we were able to study the impact of different lockdown policies and vaccination strategies. So we characterize the nodes in terms of their size and immunity distributions. So remember, households, working places, schools, and nursing homes. And methodologically, our model can be seen as a meta-population multi-scale model, able to couple biological and social dynamics. Our results show that protecting the vulnerable segment of the population would influence significantly in the reduction of deaths, whereas the reduction of contacts towards the most heterogeneous hubs would not affect the number of disease cases as much. but they are important as well for reducing the disease transmission levels. So the fact that we are working with this multi-scale approach and we are including this within host dynamics models is important because it lets us implement vaccine administration and thus to evaluate the impact of different strategies. So again, we showed that protecting the most vulnerable segment of the population is very effective. And it is important to bear in mind that there are many open research perspectives in this direction, considering epidemiological, behavioral, and economic aspects of epidemic spreading. So just to finish, a short reflection regarding human mobility that has a huge effect on the spreading of infectious diseases, speed and cluster formation. And its understanding has become assertive to monitor, control, and prevent epidemic spreading. And so it is a very nice topic to explore, to understand, and to go to deepen on it. So if you have further doubts, comments, questions, suggestions, please feel free to contact me. This is my email address. So that's all, and thank you very much for your attention.